Hi class, so this section we're discussing equilibrium constants, and let's get started. So we are going to expand on the equilibrium and actually determine a value, an equilibrium constant for a reaction. So let's go back to understanding what an equilibrium is. Your book talks about a ski lift. So at the morning, a ski lift opens. There's nobody on the lift because it hasn't opened. But once it opens, you start getting skiers that go up to the top of the mountain, but there's nobody coming down. So that's the start of a reaction. You have what would be the product being pushed on, but eventually enough people will be up the lift that they'll start coming back down, and so it'll start equaling out. One group will go up, the others will go down, and eventually it'll be an equilibrium. And this is very similar to reactions. I found this little gift, but I don't really like it as much, but you can see where it goes back and forth because you should still have product here. Not all of it will go back. So that's the only thing, and I couldn't find anything to try to add it in. So just know that there should still be product over here, even with the reaction going back. So an equilibrium constant. This is a general formula for excuse me. I can't talk today. A general formula for an equilibrium constant. The A's, the capital A, so this would be a balanced equation. And so the capital A's will be our substances. It will be our reactants, A and B, capital, and C and D would be our products, so our chemical formulas. The small alphabet letters, A, B, C, and D, are the coefficients that are in front. So for instance, you see a reaction, it's 1, 2, and if it's 1, it's left blank. These are the coefficients. And what we do here, excuse me, is we multiply the concentrations of the products together, which would be on top, divided by the concentrations of the reactions. These brackets mean concentration, so we're going to be dealing with molarities here. So, and then if you look here, the little numbers, the little letters of the alphabet, the small letters, are the coefficients. So if there's a coefficient here, we now change it into an exponent on here. If it's a 1, we leave it blank. And Kc means equilibrium constant. So let's get started. The best way to learn is to actually put it into action. So here we're given a balanced equation, and we want to write out the equilibrium constant for this. So we're going to use this information and end up writing it out like this. So what do we need? We need the equation, we need the equilibrium expression, and we need to know how to set up the concentrations of the products over the reactants. So here we have the balanced equation, and we have the equilibrium expression. So again, products are on top in brackets, not parentheses, brackets. Brackets mean concentration. So we take the CO2 and we take CO down here and we put O2 down here. But we're not finished because we need, excuse me, we need to actually add the coefficients, which we do not have on here. So we have to look. CO has a 2. Oxygen has a 1, so we just leave it blank as a default. And CO2 has a 2, which we put here. So we have now written out the equilibrium expression for the reaction. Now, we're going to go a step further, and we're going to look about calculating the equation. So if we look here, we have a balanced equation, and it's already been filled out with the equilibrium constant. But what if we had plugged in our molar concentrations? So not only given the expression, but given molar concentration for these to actually plug into the coefficient, the equilibrium constant. So if we were to plug in values, so here you're given different, so hydrogen is a reactant, iodine is a reactant, and then we have hydrogen iodide as a product, and then we're given the balanced equation. However, if you notice that these are all at different concentrations, this is all at different concentrations, this is all at different concentrations, but we're given this at a certain temperature of 427 degrees Celsius. Something interesting happens, that at this temperature, we always end up with a value, an equilibrium constant of 54. Regardless of what the concentrations are, as long as these are balanced out, meaning equal to each other in proportion of what they should be, I should say proportional to each other, we end up with 54, regardless of the different concentrations. So what has been determined from this is that A reaction at a specific temperature can only have one value for an equilibrium constant, meaning that at this temperature, we're always going to end up with this value if the concentrations of the reactants and the products is in proportion to each other the way it should be. So that's something that's interesting to all of this. Now let's take a step back. So let's take a step forward here. So for example, the concentrations of each species in experiment 1, the concentration for hydrogen is 0.10 molar, iodine is 0.20 molar, and hydrogen iodide is 1.04 molar. So when we plug these in, we end up with 54. Excuse me, in 2 and 3, we have even more different concentrations, and yet we still end up at 54. So this is exactly what I just stated, that at specific temperatures, there should only be one value at that to find for the equilibrium constant. Okay, so let's take a look at another problem. The decomposition of dinitrogen tetroxide forms nitrogen dioxide. Here we have a balanced equation. What is the numerical value of the equilibrium constant at 100 degrees Celsius if a reaction mixture at equilibrium contains 0.45 molar and 0.31 molar? So what we have to do, let's take a look at this first step. We need to determine the molarities of our reactants and our products. We need the equilibrium constant. We need the expression for it, the formula, and we're going to need the equation in order to plug this in. So the second step is to write the expression out. So we take products are always on top, reactants are always on the bottom, and we need a coefficient. So this one does not have a coefficient, so we leave it off. But we have a coefficient here, so we take the 2. The third step is now we have to plug in the correct molarities for the correct product and the correct reactant. So let's start here. We have 0.45 molar. This is a reactant, so that one's going to go on the bottom. This 0.31 molar is a product. We're going to put it at the top. Now, there's a few things you need to remember here. All of a sudden, my voice and my throat are acting up. If you do not remember the coefficients, you will always mess this up. If you do not put the correct molarities or concentrations on with the correct product and reactant, it is very easy to mess these simple equations up. So make sure you check and double check these things. I always suggest following these steps and not shortcutting it by putting brackets and just the molarities in, because you will mess up simple things like coefficients. And all it takes is to mess up one coefficient as an exponent, and now your whole problem's wrong. So plugging these in, it gives us an equilibrium constant of 0.21. This is our value that we're trying to determine. Now let's do another one. So what is the numerical value of the equilibrium constant at 443 degrees Celsius if the equilibrium concentrations are as follows? So they're giving us, and even broken down into concentration brackets, the molarity for these substances. So the next thing we need to do is we need to plug everything in. So this moved on me, and we have our information of the molarities and the substances. We need the equilibrium constant, the formula, and we have the balanced equation. So let's start plugging everything in. So here we take the products are always on top with the coefficient, and then we have our reactants, and they're 1-to-1 at the bottom. Next step, plug in the concentrations. So we have our product with an exponent of 2, and then we have our reactants concentrations. And this produces an equilibrium constant of 8.5 times 10 to the negative 2. And that's it. Thank you.